Hello everybody. Today we are discussing about the fragmentation patterns of phenols and ethers. Regarding phenols, simple phenols give strong molecular ions, and for them the molecular ion peak is so strong that they themselves is the base peak. So normally we don't see that in the case of mass spectrometry. Normally there will be for almost every other compounds the molecular ion peaks will be very much weak, but in the case of phenols they are so strong that they themselves are the base peak. And there are two other main types of fragmentation, that is M-28 peak will be there and M-29 peak will be there. M-28 is obtained by the loss of carbon monoxide and M-29 is obtained by the loss of CHO. Okay, so let's see the fragmentation patterns of phenol, how these two peaks are obtained. This is phenol OH dot plus I'll write it as a bond so that the breaking can be shown easily. This is phenol dot plus, this is the molecular ion with M by Z value is equal to 94. The molecular weight of phenol is 94. So the molecular ion gives M by Z value of 94 and this is the base peak. Okay, and now see the fragmentation. Here the bond breaks like this to give see here a double bond has been formed between carbon and oxygen. Here one bond is broken and therefore a double bond is formed, and here there is a radical dot and H dot. H dot is also there. Here also this homolysis has taken place. So these combine to give a bond and the dot plus remain at the outside. Okay, here just the rearrangement of the this hydrogen and everything has taken place. So we are getting a species like this. From here, what happens is, here I'm not writing this one, I'm not showing this one because it is understood that here one hydrogen, in fact there are two hydrogens present. One was already there and another one has been introduced now. And from here, it's interesting to see that this bond shifts to this carbon atom, and as a result this bond shifts to this CO, in between CO bond. The end result is the elimination of carbon monoxide molecule to give phenol has 6 carbon atoms. Now it has reduced to 5 carbon atoms and the bonds are like this. And here there are 2 hydrogens already there. Okay, there were 2 hydrogens here. There is no change for that, and dot plus remained in the outside, and the change here is the elimination of carbon monoxide. Carbon monoxide, a neutral molecule is eliminated, and as a result dot and plus remains on the molecule itself. And so this peak, this fragment has the M by Z value of 66. This one has the M by Z value of 66, and this is the M-28 peak which is being mentioned over here. This is the M-28 peak by the loss of carbon monoxide. Okay, hope it is clear. Carbon monoxide is eliminated. And we should get this M-29 also. That means there is a difference of only one hydrogen. So here we can clearly see that from here, one of the hydrogens will be gone out to get H dot and the remaining one as positive. This species is cyclopentadienyl cation and this one has M by Z value of 65, and this is the M minus 29 peak. Okay, so let me tell you once again that the base peak of phenol, simple phenol, is 94, and which is the molecular ion peak itself. And there are two other prominent peaks are M minus 28 peak and M minus 29 peak. M minus 28 is obtained by the elimination of carbon monoxide, and from there again one hydrogen eliminates to give M minus 29 peak. And suppose if the phenol has any alkyl side chain, they undergo benzylic fission. They undergo benzylic fission to give hydroxy tropylium cation. Let's see the fragmentation. For example, phenol with OH group, phenol with alkyl side chain. The simplest example could be this one. This is, what is this molecule? This is paracresol, right? So instead of just paracresol, we are writing the mechanism with a general example so that it could be applicable to all the compounds which contain such types of bonds. So this is CH2R. Okay, this is a general example. The simplest one of this kind is paracresol, but there could be any other group as a side chain. Okay, so this is the simplest example. From here, dot plus I have given. Okay, this will be the molecular ion, and we don't know, we cannot say the molecular ion, the M by Z value of this molecular ion, because we have taken an arbitrary compound, right? So these R could be different, therefore the mass value can also be different. So in the fragmentation pattern, from a dot plus, we can say that anything can be plus, and from there two daughter fragments will be there, in which one will get the dot and the other will get the plus. In that sense, I can write it like this, that R dot, one mode of fragmentation will be R dot and the remaining one as plus. Okay, R dot and okay, we obtain two fragments in which one is the radical and the other is a cation, an ion. Okay, from here there is a rearrangement takes place, and the product is this one, hydroxy tropylium cation. OH, sorry, tropylium cation, you will be writing like this, positive charge, right? This is the hydroxy tropylium cation. Its M by Z value is 107. Its M by Z value is 107. Okay. Here also this fragment also will have the same M by Z value, but that one on rearrangement gives you the peak at M by Z value 107. This is the most important peak. So therefore this is the base peak when it comes to phenols with alkyl side chains. And you'll be wondering how we obtained, or how this rearrangement took place. Let me explain. One, two, three, OH, CH2. Right. Here is a positive charge. Let me number these carbon atoms for a better understanding. That 1, this is the second carbon, 3, 4, 5, 6 and 7. Okay. Now this 7, the bond between second and seventh carbon breaks, and it is attached to the first carbon. Okay, now the situation is it's like this, that is, here this is the CH2, I'm writing it like this so that I can rearrange it in the next step. And here what are there is no change for all these things, these are intact, and the numbering is, again, this is 1, 2, 3, 4, 5, 6 and 7. And a change to be noted is that the positive charge has shifted from first carbon to second carbon because its bond is broken, right? So there is a positive charge in the place of second carbon now. It was in the first carbon, now it has shifted to second. Again the position is changing. That is to make up for the loss of the carbon, or to make up for the electron loss in the case of second carbon atom. Hydrogen from here is shifted to the second carbon atom to give a species like this. Sorry, I forgot to give the OH group here. And now the bonds position is like this. Okay. The position of bonds are, what is the condition now? It is here, it is downwards, and here is another bond, and there are 3 bonds, 5 bonds, no problem. And here the first carbon, here is the CH, and the positive charge is shifted again to the first carbon now. Okay, this is nothing but, see, I'll number it once again, that this is first, second, third, fourth, fifth, sixth and seventh, and finally this is equivalent to our hydroxy tropylium cation. We can write it in the more familiar way. Okay, OH. Okay, so again, I hope you understood. I'll number it again. 1. Oh, sorry, it's a little bit different. Okay, so I'll write it again. Double bond, I had messed up with the position of the double bonds. So this is OH, and here is the positive charge. Okay, now it is fine, I think. Let me number 1, 2, 3, 4, 5, 6 and 7. Yeah, now this is perfectly all right. You can see that there is a double bond between second and third carbon. I have given between fourth and fifth is there, and between sixth and seventh carbon is there, and there is a positive charge on the first carbon atom. This is how the rearrangement is taking place, and therefore this is the base peak, and the most stable peak and the most abundant peak. Now let's see what happens with ethers. We are checking the case of aliphatic ethers first. They exhibit weak molecular ion peak. Okay, their molecular ion peak is rather weak. We had seen strong molecular ion peak in the case of phenol, but it is weak in the case of this aliphatic ethers. The common fragmentation patterns are alpha cleavage and beta cleavage, in which beta cleavage is the prominent one. Okay, the beta cleavage is the prominent one. Here, the largest alkyl group is expelled. If there are 3, and in the beta carbon, if there are 3 alkyl groups, the largest alkyl group will be expelled as radical. That is the common mode of fragmentation in almost all the others. We have seen in the case of alcohols and all, alcohols, alkanes, etc. The largest alkyl group is more likely to be expelled as radical than the smallest one. Okay, here we can write the fragmentation by taking a general example, that is carbon. There are 3 bonds. It is bonded to oxygen. Again, it is bonded to a carbon which has 3 other bonds, and here is the dot and plus. For the sake of convenience, we can write the dot and plus outside the molecule, or it could be on the actual atom from where the electron is expelled. So that depends upon our convenience to show the fragmentation pattern. So I'll be using both. In some cases, I'll be writing the dot and plus on the particular oxygen atom, or otherwise in some other cases I'll be writing it on the outside. So that all those things depends upon the easiest way to show how these fragments are formed. Okay, and now we can name them. That is, this is the oxygen, so this could be the alpha carbon. In the case of this ether, there are 2 alpha carbons, and these are the beta positions, beta, 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 and here also there will be 3 beta positions, right? And whatever we have told you, that largest alkyl group is expelled as radical. So suppose this is the alkyl group, largest alkyl group present. Okay, there could be other alkyl groups, and this is the largest one. And how this takes place, what happens here? Here this bond breaks like this, R dot. Okay, and you will be getting a structure like this. Here are the 2 beta positions, and there is a single bond O plus, and this is the newly formed double bond, right? This is the newly formed double bond, and this are the 2 branches, and this is called oxonium ion. C double bond O plus ion is called oxonium ion. And see the next point, if the oxonium ion contains a beta hydrogen, alkane is eliminated. If the oxonium ion doesn't contain a beta hydrogen, the fragmentation stops here. But if there is another beta hydrogen present, alkane can be eliminated. For that, we can write beta hydrogen. For beta hydrogen, we can write a group here like this, CH3 group. We can write a CH3 group here, and now we can show the fragmentation. Here this bond breaks, this bond breaks, this one breaks, and this one goes here. That is, 2 bonds are broken. O C bond is broken, and and CH bond is also broken, and the products are C, there is no change for that. Double bond O plus, again there is no change. Instead of this carbon bond, here 1 hydrogen has come. That's one change. And here, what are the remaining ones? There are 2 bonds over there, single bond, 2 hydrogens. That also can be any other groups also. Since it is hydrogen here, I'll write it as hydrogen itself. And now, see, there is a double bond formed, a newly formed double bond. This is how the alkenes are eliminated, and again C double bond O plus H, this ion is formed. Okay. When it comes to alpha cleavage, the fragmentation is very much simple. We can write it like this. That is R O R dash. R O R dash is our ether. Here is the molecular ion dot plus. It can be fragmented into 2 ways. That is, one is R dot and O R dash plus, or the other way is, the second way is R plus and O R dash dot. So it could be cleaved as one should get the positive one. There will be 2 fragments. One will get a radical part and the other will get a positive part. So there are 2 possibilities. And now let's see the example of diethyl ether. I'll discuss the alpha cleavage first, because it is written above. So diethyl ether is C2H5 O C2H5 dot plus. So the molecular ion peak, this is the molecular ion peak with MZ value is 74. Okay, MZ is 74, and see R dot is C2H5 dot. In the first example, C2H5 dot and C2H5O plus will be formed. Okay. In the second example, the possibility is C2H5 plus and again C2H5O dot. In the case of this one, C2H5O plus M by Z is equal to 45. So So only positive charges will be detected. Here, this is the ethyl group. We know that its M by Z value is at 29. Okay, so the peaks obtained are M by Z value is equal to 45, M by Z value is equal to 45, and M by Z value is equal to 29. Now let's see the beta cleavage. Okay, so to write the beta cleavage, CH2O, CH2, CH3. This is the beta position, and this is dot plus. This is the alpha position, and this is the beta position. Okay, this is, since it is symmetrical, we can show only one. And here the fragmentation is like I have shown. Okay, here an oxonium ion is formed like this, that is CH2 double bond O plus CH2 CH3. Okay, this is clear. CH2 alpha by that one. What is eliminated? CH3 dot is eliminated, and the remaining one is the oxonium ion obtained is this one. Okay, the M by Z value of this peak is at 59. The M by Z value of this peak, sorry, this fragment is at 59. Now, you should remember that in the case, if there is a beta hydrogen, again fragmentation takes place and alkene will be eliminated. You can see a beta hydrogen here. That is CH2H. There is a beta hydrogen like this, right? So this is the alpha carbon, this is the beta carbon. Now see, the bond breaks here and it goes like here, this one and this one, and see, there is an elimination of ethylene molecule, and the remaining ones are CH2 double bond O plus H. Okay, this H dot has attached to this oxygen plus, and the remaining one is an ethylene. Ethylene molecule is eliminated, and the M by Z value of this fragment is that M by Z is equal to 31, and this is the base peak. Okay, and this is the base peak. This is the base peak. M by Z at 31 is the base peak. And in the case of diethyl ether, I'm revising it. That is, there are, first peak is the molecular ion peak, and you will obtain it at M by Z is equal to 74. And the second one is the most prominent fragmentation is the beta cleavage. And the first fragment obtained in beta cleavage is that M by Z is equal to 59. First it was 74, and now it is M by Z is equal to 59, and then it is fragmented into the base peak, which is that M by Z is equal to 31. Okay, 3 peaks were obtained, and now rather like less visible peaks are M by Z is equal to 45. That's because of C2H5O plus ion, and M by Z is equal to 45 is because of C2H5O plus ion, and M by Z is equal to 29 is because of ethyl cation C2H5 plus. Okay, these are the different fragmentation products obtained in the case of diethyl ether. Let's take the example of anisole and explain the fragmentation of aromatic ethers. Anisole is nothing but methylphenyl ether. So there will be OCH3 group on top, OCH3. This is anisole dot plus, and in the first mode, one formaldehyde molecule is eliminated. HCHO is eliminated. You can see there is a bond like this, OCH3, right? So OCH2H is there. If you write like that, you are cutting this much part. So what will be remaining? just hydrogen, sorry, not O. Only hydrogen will be remaining over there. Only hydrogen will be remaining over there. So let's write that. Neutral formaldehyde molecule is eliminated and you'll get one hydrogen is present over there, and here dot and plus are remaining because formaldehyde, a neutral molecule is eliminated. So the remaining fragment will have both dot and plus, and this is actually M minus 30 peak. Okay, the molecular weight of formaldehyde is 30, so this is M minus 30 peak, and this is at M by Z is equal to 78. The M by Z value is at 78. Now, since it's a species having a dot and plus, let's split it in such a way that H dot and the remaining plus is obtained. So, on fragmentation again, you will get like this. It's rather a rare species in which benzene ring is having a positive charge. So the M by Z value of this one is at 77, and this is the base peak. This is the base peak of anisole, and this is the first mode of fragmentation, that is by the elimination of neutral formaldehyde molecule. Let's see the second mode, in which that's normal one, like there will be an alkyl group dot and the remaining one as plus. So we can write like this, that is CH3 dot and the remaining one as a positive charge. Therefore, we'll be getting a species like this, O plus. And now see here, this bond goes here, and as a result I'll write it with another color so that you can understand it in a better way. That is, this bond is shifted to this carbon and this bond is shifted to this carbon. So what happens? The ring size has been reduced from 6 carbon atom to 5 carbon atoms. Okay, I think it's not clear. I'll write it again. Okay, I'll write it again. The double bond is written here like this, and O plus is here, and see, this double bond is shifting to in between this CO bond, and therefore this bond, this CC bond, is shifted to this carbon atom. Okay, and therefore whatever you will be getting is a species like this. From 6-membered it has reduced to 5-membered ring, and this carbon contains a CO group now. Okay, now it's clear because this bond is shifted to this side and there is a CO group. Now this CO is eliminated. Carbon monoxide is eliminated, and as a result, the resultant species will have a positive charge. Okay, the resultant species will have a positive charge, and the M by Z value of this one is at 65. Okay, this is the fragmentation of anisole. The peaks obtained are the molecular ion peak, and there is a peak of M minus 30 peak, that is at M by Z is equal to 78, and there is a base peak at M by Z is equal to 77, and one more peak is at M by Z is equal to 65. The aromatic ethers which have a larger alkyl group other than methyl groups, if there is a larger alkyl group present, there is a possibility of one more peak, that is the beta hydrogen transfer is taking place, and therefore we'll get another peak. So let's see that by taking the example of phenol. Phenol is, instead of methyl group, there will be an ethyl group present. Okay, O CH2 CH3 is phenol. Now we are writing it in such a way that it is understood properly. Okay, CH2 CH2H. So this is the molecular ion P. This is nothing but C6H5O C2H5. Okay, ethyl phenyl ether, or otherwise known as phenitol. Okay, TOLE, otherwise known as phenitol. Now see the fragmentation. A bond breaks like this, and this bond breaks, and as a result you will be getting OH dot plus, and a neutral molecule is, what is a neutral molecule? Ethylene molecule, that is C2H4 is eliminated as neutral one, and the remaining one is at OH dot plus, and the MSc value of this species is, we know, we have seen in the case of phenol that it will be at 94. And now from here carbon monoxide, a neutral carbon monoxide eliminates, and to give a species like this with MSc is equal to 66, and again by the elimination of H dot you will end up the species this one. Sorry, there's a small correction here, it was like dot plus, right? So 66 dot plus, and then H dot is eliminated to give a species like this with MSc is equal to 65. I'm not writing the fragmentation pattern from here to here because that I have discussed in the first part of this video, that is the fragmentation pattern of phenol. Okay, if you are not clear with that again, please go through that first part again and watch. Then you will get a clear idea that how do these peaks are obtained, that MSc is equal to 66 and 65, that's already explained. So with this I'm stopping here, and in the next videos and classes I'll be discussing the fragmentation patterns of carbonyl compounds. Thank you.